A Brief History of Time, written by Stephen Hawking, read by Akashveer. Chapter 6, Black Holes, Part 2. In order to understand what you would see if you were watching a star collapse to form a black hole, one has to remember that in the theory of relativity there is no absolute time. Each observer has his own measure of time. The time for someone on a star will be different from that for someone at a distance because of the gravitational field of the star. Suppose an intrepid astronaut on the surface of the collapsing star, collapsing inward with it, sent a signal every second, according to his watch, to his spaceship orbiting about the star. At some time on his watch, say 11, the star would shrink below the critical radius at which the gravitational field becomes so strong that nothing can escape, and his signals would no longer reach the spaceship. As 11 approached, his companions watching from the spaceship would find the intervals between successive signals from the astronaut getting longer and longer. But this effect would be very small before 10:59:59. They would have to wait only very slightly more than a second between the astronaut's 10:59:58 signal and the one that he sent when his watch read 10:59:59. But they would have to wait forever for the 11 signal. The light waves emitted from the surface of the star between 10:59:59 and 11 by the astronaut's watch would be spread out over an infinite period of time as seen from the spaceship. The time interval between the arrival of the successive waves at the spaceship would get longer and longer, so the light from the star would appear redder and redder and fainter and fainter. Eventually, the star would be so dim that it could no longer be seen from the spaceship. All that would be left would be a black hole in space. The star would, however, continue to exert the same gravitational force on the spaceship, which would continue to orbit the black hole. This scenario is not entirely realistic, however, because of the following problems. Gravity gets weaker the farther you are from the star. So the gravitational force on our intrepid astronaut's feet would always be greater than the force on his head. This difference in the forces between would stretch our astronaut out like spaghetti or tear him apart before the star had contracted to the critical radius at which the event horizon formed. However, we believe that there are much larger objects in the universe, like the central regions of galaxies, that can also undergo gravitational collapse to produce black holes. An astronaut on one of these would not be torn apart before the black hole formed. He would not, in fact, feel anything special as he reached the critical radius. He could pass the point of no return without noticing it. However, within just a few hours, as the region continued to collapse, the difference in the gravitational forces on his head and his feet would become so strong that again it would tear him apart. The work that Roger Penrose and I did between 1965 and 1970 showed that, according to general relativity, there must be a singularity of infinite density and space-time curvature within a black hole. There is rather like the Big Bang at the beginning of time, only it would be an end of the time for the collapsing body and the astronaut. At this singularity, the laws of science and our ability to predict the future would break down. However, any observer would remain outside the black hole would not be affected by failure of predictability, because neither light nor any other signal could reach him from the singularity. This remarkable fact led Roger Penrose to propose the cosmic censorship hypothesis, which might be paraphrased as God abhors a naked singularity. In other words, the singularities produced by gravitational collapse occur only in places like black holes, where they are decently hidden from outside view by an event horizon. Strictly, this is what is known as the weak cosmic censorship hypothesis. It protects the observers who remain outside the black hole from the consequences of the breakdown of predictability that occurs at the singularity, but it does nothing at all for the poor unfortunate astronaut who falls into the hole. There are some solutions of the equations of general relativity in which it is possible for our astronaut to see a naked singularity. He may be able to avoid hitting the singularity and instead fall through a wormhole and come out in another region of the universe. This would offer great possibilities for travel in space and time, but unfortunately it seems that these solutions may all be highly unstable. The least disturbance, such as the presence of an astronaut, may change them so that the astronaut could not see the singularity until he hit it, and his time came to an end. In other words, the singularity would always lie in his future and never in his past. The strong version of the cosmic censorship hypothesis states that in a realistic solution, the singularities would always lie either entirely in future, like the singularities of the black holes or gravitational collapse, or entirely in the past, like the Big Bang. It is greatly to be hoped that some version of the censorship hypothesis holds, because close to naked singularities it may be possible to travel into the past. While this would be fine for writers of science fiction, it would mean that no one's life would ever be safe. Someone might go into the past and kill your father or mother before you were conceived. The event horizon, the boundaries of the region of space-time from which it is not possible to escape, acts rather like a one-way membrane around the black hole. Objects such as unwary astronaut can fall through the event horizon into the black hole, but nothing can never get out of the black hole through the event horizon. Remember that the event horizon is the path in the space-time of light that is trying to escape from the black hole, and nothing can travel faster than light. One could well say of the event horizon what the poet Dante said of the entrance to hall: all hope abandon, ye who enter here. Anything or anyone who falls through the event horizon will soon reach the region of infinite density and the end of time. General relativity predicts that heavy objects that are moving will cause the emission of the gravitational waves, ripples in the curvature of space that travel at the speed of light. These are similar to light waves, which are ripples of the electromagnetic fields, but they are very much harder to detect. Like light, they carry energy away from the objects that emit them. One would therefore expect a system of massive objects to settle down eventually to a stationary state, because the energy in any movement would be carried away by the emission of gravitational waves. It is rather like dropping a cork into the water. At first it bobs up and down a great deal, but as the ripples carry away its energy, it eventually settles down to a stationary state. For example, the movement of Earth in its orbit around the Sun produces gravitational waves. The effect of the energy loss will be to change the orbit of Earth so that gradually it gets nearer and nearer to the Sun, eventually collides with it and settles down to a stationary state. The rate of energy loss in case of Earth and Sun is very low, about enough to run a small electric heater. This means it will take about 1,000 million years for Earth to run into the Sun, so there is no immediate cause for worry. The change in the orbit of the Earth is too slow to be observed, but this same effect has been observed over the past few years occurring in the system called PSR 1913 plus 16. PSR stands for pulsar, a special type of neutron star that emits regular pulses of radio waves. The system contains two neutron stars orbiting each other, and the energy they are losing by the emission of gravitational waves is causing them to spiral in towards each other. During the gravitational collapse of a star to form a black hole, the movements would be much more rapid, so the rate at which the energy is carried away would be much higher. It would therefore not be too long before it settled down to a stationary state. What would this final stage look like? One might suppose that it would depend on all the complex features of the star from which it had formed. Not only its mass and rate of rotation, but also the different densities of various parts of the star, and the complicated movements of the gases within the star. And if black holes were as varied as the objects that collapse to form them, it might be very difficult to make any predictions about black holes in general. In 1967, however, the study of black holes was revolutionized by Warner Israel, a Canadian scientist who was born in Berlin, brought up in South Africa, and took his doctoral degree in Ireland. Israel showed that according to general relativity, non-rotating black holes must be very simple. They were perfectly spherical, their size dependent only on their mass, and any two such black holes with the same mass were identical. They could in fact be ascribed by a particular solution of Einstein's equations that had been known since 1917, found by Carl Schwarzschild shortly after the discovery of general relativity. At first, many people, including Israel himself, argued that since black holes had to be perfectly spherical, a black hole could only form from the collapse of a perfectly spherical object. Any real star, which would never be perfectly spherical, could therefore only collapse to form a naked singularity. There was, however, a different interpretation of Israel's result, which was advocated by Roger Penrose and John Wheeler in particular. They argued that the rapid movements involved in a star collapse means that the gravitational waves it give off would make it ever more spherical, and by the time it had settled down to a stationary state, it would be perfectly spherical. According to this view, any non-rotating star, however complicated its shape and internal structure, would end up, after gravitational collapse, as a perfectly spherical black hole whose size would depend only on its mass. Further calculations supported this view, and it soon came to be adopted generally. Israel's result dealt with the case of black holes formed from non-rotating bodies only. In 1963, Roker, a New Zealander, found a set of solutions of the equations of general relativity that described rotating black holes. These Kerr black holes rotate at a constant rate, their size and shape depending only on their mass and rate of rotation. If the rotation is zero, the black hole is perfectly round and the solution is identical to the Schwarzschild solution. If the rotation is non-zero, the black hole bulged outwards near its equator, just as the Earth or the Sun bulged due to rotation. And the faster it rotates, the more it is bulged. So, to extend Israel's result to include rotating bodies, it was conjectured that any rotating body that collapsed to form a black hole would eventually settle down to a stationary state described by the Kerr solution. In 1970, a colleague and a fellow research student of mine at Cambridge, Brendan Carter, took the first step towards proving this conjecture. He showed that provided a stationary rotating black hole had an axis of symmetry like a spinning top, its size and shape would depend only on its mass and rate of rotation. Then in 1971, I proved that any stationary rotating black hole would indeed have such an axis of symmetry. Finally, in 1973, David Robinson at King's College, London, used Carter's and my result to show that the conjecture had been correct. Such a black hole had indeed to be the Kerr solution. So, after gravitational collapse, a black hole must settle down into a state in which it would be rotating, but not pulsating. Moreover, its size and shape would depend only on its mass and rate of rotation, and not on the nature of the body that had collapsed to form it. This result became known by the maxim, "A black hole has no hair." The no-hair theorem is of great practical importance because it so greatly restricts the possible types of black holes. One can therefore make detailed models of objects that might contain black holes and compare the predictions of the model with observations. It also means that a very large amount of information about the body that has collapsed must be lost when a black hole is formed, because afterwards all we can possibly measure about the body is its mass and the rate of rotation. The significance of this will be seen in the next chapter. Thank you very much for watching. If you want some more videos like this one, please like, share and subscribe to my channel. Have a great day. Stay home. Stay safe.